Okay, welcome back. Let's have a look at the structure of atoms, starting with chapter 6. So a quick overview of the chapter, we'll be looking at electromagnetic radiation, quantization, such as taking into consideration the theories of Planck, Einstein, also looking at energy and photons. Talking about atomic line spectra and Niels Bohr, we'll be talking about particle wave duality as a prelude to quantum mechanics, although only very briefly and in limited detail. We'll be looking at the modern view of electronic structure, wave or quantum mechanics. We're looking at the shapes of orbitals and then looking at a final electron property, the electron spin. So atomic structure, we have different models describing the structure of atoms. When atoms react, it is the electrons that react. I mean, the electrons form the outer parts of our atoms, whereas the protons and neutrons are in the nucleus, the electrons sort of exist diffusely around that nucleus. And so those are what we'll use whenever we do chemical reactions. And so much of our understanding of electrons comes from analysis of the absorption or emission of light. Electromagnetic radiation, this is where atoms gain energy and they become excited. So if we have some atom A, and then we add to it energy, which will give the letter E, just for consistency later on, that will go to this A star or A asterisk, like so. And this will be what we will sort of like deem the excited atom. And now it's got more energy, it's might be vibrating more, it might be moving around faster, things like that. So this added energy is absorbed by electrons and then released in the form of electromagnetic radiation, or as we commonly call it, light. Now, not all of this light is visible to us because our eyes only have a particular wavelength or wavelength range, but there are many different types of light. From infrared light through X-rays, gamma rays, UV rays even as well. Some light in the UV region we can actually see as well, but only a limited amount. So energy traveling through space is basically what light is. It has some energy associated with it. Particles are waves. We'll talk about this more later. This is the equation which will help us to relate the frequency to the wavelength. Don't worry yet if you don't know what frequency and wavelength mean. We'll talk about those. And then C is our speed of light. So C is the speed of light, usually 2.998 times 10 to the 8 meters per second, or sometimes 3.00 times 10 to the 8 meters per second. We also have lambda, the wavelength. This is typically in nanometers, at least for visible light. Some things like radio waves can be a lot longer. And then here, nu, so this is not B, this is the Greek letter nu, is equal to the frequency. So nu is in terms of per second or hertz. So really this is the number of waves per second. So electromagnetic radiation or light consists of oscillating electric and magnetic fields traveling through space. And they travel at the same rate, i.e. the speed of light in a vacuum. Typical units that we use, so for example, C is the speed of light, 3.00 times 10 to the 8 meters per second. That's just to 3 significant figures. Earlier we saw it to 4, but if we move to 3, we have to round up a little bit, and so that's why it becomes 3. Typically, this is the form that we'll use most often. But we can, this unit here, this is meters /second, so this is meters per second. And here we have meters seconds to the -1. This is still meters per second. These are the same units. Nu is in terms of per second or cycles per second or hertz. Lambda, the wavelength, is equal to distance. So it's got nanometers or meters in the case of radio waves. Visible light typically in nanometers, which is 10 to the -9 meters. Electromagnetic radiation then, or light, is composed of 2 orthogonal vectors. Here is a drawing of an electric wave and a magnetic wave. So the electrical wave is this blue line called the electric vector, and this red line here is the magnetic vector, both of which have something called an amplitude, which is basically just the height of that wave, and it corresponds somewhat to the intensity of the wave. If we then look at the wave, for example, here, this, following this blue line here, which I've tried to trace with my red line, this is one wavelength here. So it's going from, this is the starting point, back to what would be the starting point of the next wave. That is a wavelength. We can also measure it from, for example, peak to peak or trough to trough. And then at this point here where we have a zero value in the amplitude, we have what is called a node. So this is where it goes from negative amplitude to positive amplitude. We have a node, this 0 point, where the wavelength is zero. And this is a function, or this is a property of both quantum and classical waves, like acoustic waves. And so it's these wavelengths, the number of these per second, which is our frequency. Electromagnetic radiation can have different wavelengths. So for example, here we have visible light, we have ultraviolet radiation. If these are on the same sort of axes, then, or the same scale, then we have, for example, a wavelength here in visible light, which is much longer than the wavelength that we have in ultraviolet radiation. Now, the amplitude may be quite similar, but the number of waves per second, or the frequency, is going to be much higher. They both have nodes. Their line shapes are pretty similar. So the intensity of light is a function of the wave's amplitude. A point of zero amplitude is called a node. Light is characterized by its wavelength and frequency. So again, wavelength is this distance between the two peaks, or the full wave, both positive and negative parts. And the frequency then is how many of those happen per second. Things like waves in the sea, ocean waves, those can also be described in a similar manner. Now, their wavelengths may vary, the intensity may vary, the frequency may vary, but they follow a pattern which is quite reminiscent of the similar sort of waves that we get in electromagnetic radiation. And then we have the full electromagnetic radiation spectrum. It covers a huge range of energies, frequencies, and wavelengths, but we go from, like, for example, radio waves. Down here we've got our FM and our AM radio waves that we might listen to in our cars, or radios in our homes. Microwaves then that we could use to heat our food. Infrared radiation, which are heat lamps, or they're used also in modern surgery, just as sort of disinfectant type things. UV rays, then we know about those come from the sun, some of which can be dangerous. X-rays, medical use, they also have use in security in airports. They also have use in science, in determining the structures of different compounds. And then gamma rays over here, which are very high energy, typically used for things like pathogen removal in food, or fundamental science as well. Very high energy. So this scale from long wavelengths, so you can see here more than tens of meters in long radio waves, right down to 10 to the minus 16 meters, so much less than a nanometer. As these wavelengths decrease, we also increase the frequency, so the number of waves per second, and this corresponds to an energy increase, and we'll see shortly how we can interrelate these things. The visible spectrum then is just a really small portion. So the visible spectrum is really to do with human bias. It's what we can see, so we call it visible spectrum. Other animals see different regions of the spectrum. So this part here is all that we see with our naked eye. And these different light colors actually correspond to different energies. So red light, for example, has a long wavelength, around 700 nanometers, and has a lower energy than the blue light, which has a high frequency and is higher in energy. So the visible region of the electromagnetic spectrum is only a small portion of the entire spectrum. All right, let's do a sample calculation. Let's try and do this. So what is the wavelength of the radio waves from the WOXY 97.7 megahertz radio station. So knowing that we have this equation here, C is equal to the frequency times the wavelength, and M in the megahertz is 10 to the 16, what is going to be the wavelength, i.e. lambda, of the radio waves from WOXY? Give you 10 or 15 seconds to try and answer this. Remember, of course, you can always pause to get more time. Remember, pause to get more time. Answer coming soon. Okay, so the first thing that we need to do is we know the speed of light is, so C is equal to, it's just a constant, it doesn't change. 0.0, speed of light in a vacuum, times 10 to the 8 meters per second. Okay. We also know the frequency, nu, is equal to 97.7 times 10 to the 6 per second, second to the minus 1. So we rearrange this equation and we get lambda is equal to C over nu. So that's going to be equal to 3.00 times 10 to the 8 times 10 to the 8 meters second to the minus 1 all over 97.7 times 10 to the 6 second to the minus 1, which gives us a value, I think, of around about let's see, calculator, so 3.81. Something like 3.00 times 10 to the 8 divided by 97.7 times 10 to the 6. It's going to be by 307 meters. Or sorry, 3.07 meters. Our units then, so this are gone. Okay. So it's by 3.07 meters is the wavelength of our radio waves from WOXY. And so these are just like, so this is how we would form our new equation. And then of course, using this for reference. Okay, so some time ago, more than 100 years ago, two scientists, Niels Bohr and Max Planck, discovered this idea of quanta, and this idea that these subatomic particles, these subatomic waves, had a specific energies associated with them. So we can think about this. So in our macroscopic world, it doesn't really make much sense. You know, if I was to tell you that you can drive, whenever you get in your car, it starts at 0 kilometers per hour because it's stationary. But whenever you put your foot on the accelerator, usually you go like 1 kilometer per hour, 2 kilometers, and so on. You gradually increase in speed until you reach whatever 20 or 30 kilometers per hour is necessary. But what if I were to tell you that whenever you put your foot on the accelerator, you go from 0 kilometers per hour suddenly to 5, then to 10, and then to 15, 20, and so on. Instead of going like continuously or gradually increasing, it increases in steps. it wouldn't make sense to you. Like you would be jerking like in a motion like that. It wouldn't be comfortable to ride like that. So that's exactly how things like electrons behave. They have specific energies which they can have. And this is under this idea of quanta. It's quantized. So yeah, so they discovered this about electrons in atoms, that they have very specific energies associated with them. And there's experimental evidence for this, which we will see very shortly. So in 1900, the German physicist Max Planck proposed that light, heat, and other forms of radiation come in tiny bundles, which he called quanta. It's quantized. It has some specific value. The amount of energy in a single particle, he said, depended on the frequency and can be given by the following equation. So this is E equals h nu, where E is the energy, h is Planck's constant, and nu is the frequency of the wave. And so this came to be known as Planck's equation. And h became known as Planck's constant. And it helps to relate energy to frequency and also to the wavelength, because remember the wavelength can be found using this relationship here, where the speed of light is equal to h nu, lambda nu. So the wavelength times the frequency is equal to the speed of light. So we could just fill in, if we rearrange this, we get it in terms of nu. Nu is equal to c over lambda. Right. And so that can be sort of filled in here, and we could get it in terms of the wavelength. And so this was a very important equation and will be very important. Just keep it in your mind. So quantization of energy. So this sort of continuing on, Max Planck proposed that the light waves existed as discrete packets of energy, quanta, in order to account for the prediction that an ideal black body at thermal equilibrium will emit radiation with infinite power. According to classical physics, the intensity of emitted light approaches infinity as the wavelength of the light approaches zero. This is because in classical physics, energy changes can be continuous. Whereas in what came to be known is that whenever we're dealing with sort of subatomic particles such as electrons, this is not possible. So here we can see a figure which represents the energy of the light emitted by this coil. So what happens is, as the temperature is increased, the emitted electromagnetic radiation from this heating element or filament increases in energy. So as the object is heated, the temperature increases, and the maximum of the curve moves towards the blue or ultraviolet region of the spectrum from the red portion. So you can see that there's a red part here, and then there's a darker part, and then there's red part, and then there's kind of this white part here. So what happens is that eventually it's sort of the object here becomes white hot. And this is because the light that is emitted from it, the heat energy, is in the ultraviolet region of the spectrum. So at higher temperatures, the maximum in the curve is in the ultraviolet region. The object is described as being white hot because it becomes white to us. It starts off a kind of red color and eventually becomes white whenever it gets super duper hot. And if you've ever cooked with charcoal or seen wood burning, whenever you initially start the burning process of the charcoal, it's black, right? So, but then eventually it kind of goes red. And then if it gets hot enough, it's supplied with enough oxygen, it will eventually turn white. And at that point, that's sort of when you start cooking. It's super duper hot. That is sort of a representation of what's happening here. So it starts off red. It's hot, but it's cold in terms of the energy that could be emitting. And then over time, it gets hotter and hotter and hotter until such times as it becomes white hot and the coals go white. And that is sort of when we start cooking, when that red to white transition occurs. Same thing with burning a lot of wood. Like, for example, initially the fire starts out red and eventually the coals or the wood itself starts to go white. I mean, there's still red light around it. Like, things cool down pretty quickly at that temperature, but there is like this whiteness to parts of the wood. Quantization then, packet of energy. Planck won the Nobel Prize in 1918 for his discovery in 1900. E is equal to h nu. H is this 6.63 times 10 to the minus 34 joules per second. This is a constant. You can look that up. Energy is restricted, so there can only be specific energies available. So like, for example, E is equal to h nu, E is equal to 2h nu, E is equal to 3h nu, and so on. So energy has to be quantized. Like there are only specific amounts of energy that an electron can absorb. So since h nu is small, macroscopic level energy appears to be continuous. So an object can gain or lose energy by absorbing or emitting radiant energy in quanta. A quanta of energy is the smallest unit of energy that may be exchanged between oscillators or emitted as radiation. If it is too small to be observed in the classical, it is too small to be observed in the classical world in which we live. So this is going back to our idea of an excited particle. So we had A plus E gives us the excited particle A star. So this has absorbed a quanta of energy, this one, which can also be, remember, equal to h nu. Okay, so this A star then can also emit this energy to go back to its original state, this relaxed state, plus E, which, according to Planck's relationship, can be also equal to h nu, which is a function of the frequency. So energy of radiation is proportional to frequency. So as the frequency increases, because this is a constant, the energy will also increase. So we can also get Planck's law in terms of the wavelength, which I mentioned briefly earlier. So E is equal to h nu, and nu is equal to c over lambda, which means that we have a new equation for the energy. So that's E is equal to h times c over lambda. As the frequency of light increases, the energy of the photon increases. As the wavelength of light increases, the energy of the photon decreases. So blue light, higher frequency, has more energy than red light with a lower frequency. So in the real world, then, this is kind of similar to rungs on a ladder. On a ladder, generally the steps or the rungs are equally spaced. Or notes in a piano, like we don't have a continuous change in frequency of the notes on a piano. We have very specific steps, which are used by pianists to play their music. Flip books then, so these are like little picture books that have a kind of a cartoon inside, that as you flick through it, it changes the image. So one of the ways that this can be used is through the photoelectric effect. And what's going on here is light from the sun or wherever is being turned into an electrical current. And so this electrical current can be observed, can be measured. We're very good at observing and measuring electrical currents. And so it's one of the ways that we perform most spectroscopy. We record most things is using changes in electrical current. In this is sort of what is called a photocell. So that means it's going to react in some way to light. We have here a cathode, which is made of metal, which is light sensitive. If light of sufficient energy strikes it, it will be able to emit or eject, an electron, and that ejected electron will travel from the negative cathode to the positive anode, and this movement will generate a measurable current. So right now, this light, in terms of photons, is too low in energy, and the frequency is too low to actually eject any electrons. And so this light basically just passes through the cathode and nothing really happens. We have here, we can see the frequency of the light incident on the photocell versus the current. So we have to reach some sort of critical frequency in order for the current to be registered. Here, a photocell operates by the photoelectric effect. The main part of the cell is a light-sensitive cathode. This is a material, usually a metal, that ejects electrons if struck by photons of light of sufficient energy. But if, for example, we have higher frequency light, this now has enough energy that it can cause an electron to be ejected from this cathode. So ejected electrons move to the anode and a current flows in the cell. So these electrons that have been ejected from the light-sensitive metal cathode will be sort of attracted towards the positively charged anode, and then this movement of electrons from the cathode to the anode is what is going to generate an electrical or a measurable current. And we can see here now that we've passed this threshold critical frequency, and we now have low intensity light, but it is sufficient energy to actually affect this electron ejection. When light of higher frequency than the minimum is used, the excess energy of the photon allows the electron to escape the atom with greater velocity. Such a device can be used as a switch in electrical circuits. So yeah, we can see here if we increase the intensity but not the energy of the light, then we just eject more electrons, which means that we have a higher current because more electrons, more current. So higher intensity light causes more electrons to be released from the surface. So you can see this is still of the same frequency as here, but now we have like 3 beams, so we can eject 3 electrons at a time. So we have a higher current. If higher intensity light is used, the only effect is to cause more electrons to be released from the surface. The onset of current is observed at the same frequency as with lower intensity light, but more current flows. And as well as that, for example, if we use a higher frequency, we would also increase the energy, because remember, the frequency is related to the energy. So E is equal to h nu, that's Planck's relationship, or Planck's equation, or Planck's law. This relationship, if we increase velocity, or not velocity, frequency, we would just sort of increase the speed at which the electron travels from the cathode to the anode. We would give it more kinetic energy. That excess energy would be converted to kinetic energy. Photoelectric effects. So certain metals will release eject electrons when light strikes the metal surface. The energy of the light must exceed a minimum or threshold energy for this to occur. Any excess energy beyond this minimum goes into the kinetic energy of the ejected electron. They fly away with greater velocity. So this is just a summary of the photoelectric effect. Classical theory suggests that energy of an ejected electron should increase with an increase in light intensity. But we don't actually observe this experimentally. So that's the idea of going back to your car. Your car increases gradually in speed. Actually, there are infinitesimally small changes in speed, but we don't really notice that. So classical theory for macroscopic objects like us and our cars gradually change in speed, whereas for electrons, they don't. They have specific amounts of energy that they can have in their excited states. This, however, is not experimentally observed. No ejected electrons were observed until light of a certain minimum energy is applied. If it was covered by classical theory, then enough energy, like it would still have been able to move the electron. Any amount of energy would be able to do something. The number of electrons ejected depends on light intensity, so long as the light is above a minimum energy. This minimum energy is also the ionization energy of the metal. So we've talked about ions briefly earlier. So for example, if we have a metal M plus this energy E, we can create plus, which is the cation, which is lost an electron, plus this electron. And so that electron then is the one that's going to, this is the one that's going to carry our current. And this is the ionization energy. So this energy that we've given it from the light is sufficient to turn the neutral metal into a cation plus an electron. And that electron is then what carries the current. So the photoelectric effect, so the conclusion here is that there is a one-to-one correspondence between ejected electrons and light waves. So for every packet of energy from the light, we get 1 electron, if it has sufficient energy. So this can only occur if light consists of individual units called photons. A photon is a packet of light of discrete energy, and we can obviously calculate that energy based on its frequency. The gist of the photoelectric effect was demonstrated. So far we've demonstrated that light, usually considered to be a wave, can also have the properties of particles, albeit without mass. For each metal, there is a threshold wavelength. So that threshold wavelength is the wavelength at which it will eject an electron. Cesium can emit electrons with red light, so that's lower energy if we recall. Some other metals require yellow light or even ultraviolet to emit. So ultraviolet, that's the blue side of the spectrum. That's higher in energy than the red side. So here we have a problem that we'll work through together. So with the photoelectric effect, you are an engineer that is designing a switch that works via the photoelectric effect. The metal used requires 6.7 times 10 to the 19 joules per atom to eject electrons. Will the switch work with light of 540 nanometers or greater? Why or why not? The solution here is to determine if the energy of the light is greater than the minimum threshold energy. If so, the electrons will be ejected. If not, then the switch will not work. So what we need to do here is we need to use the equations that we have, such as, Planck's equation. So E is equal to h nu. And then we need to remember that U is equal to C over lambda. And we need to convert this into an energy of joules per atom. So we know that our wavelength is 540, so we can fit it in here. So E is equal to Planck's constant times the speed of light all over lambda, which is equal to, 6.626 times 10 to the minus 36 times 10 to the minus 34 joule seconds times 3.00 times 10 to the 8 meters per second. All over our 540 nanometers, or 540 times 10 to the minus 9 meters. Okay, so then we can just calculate this out, and we will get our answer, which we'll find out on the next page. So here again, there's using that equation that I talked about. So we will find out, there we go. So that's the Planck's constant, that's the speed of light. And then this is the wavelength. And so we find out that the energy is 3.7 times 10 to the minus 19 joules, which is less than the 6.7 times 10 to the minus 19, which means that we will not have reached the threshold energy. The energy of the light is below the minimum threshold. No ejections of electrons will occur. The incident light must have a wavelength of greater than less than or equal to 297 nanometers to eject electrons. You can confirm this on your own. So think about how you might confirm that. So you have this minimum energy you need. So how do you get from this minimum energy to the wavelength? So I really encourage you to do that. That's the kind of important calculation that we'll be looking at. So intensity versus energy. So why not just shine a bright light? So think about the carnival game, or if you've ever been to the arcade, where you throw balls to knock down bottles. Which would you choose? So for example, you can have 50 Nerf balls, which are very light. And so if you throw them with a lot of strength, a lot of velocity, they would have higher momentum, which might be enough to knock the bottles down. But what if it's not? So you could have 50 balls that just bounce off the bottles and they don't knock down. Whereas you could throw a baseball, and so long as you're accurate, you could knock down a lot of bottles because of the sort of the mass of the baseball is much higher. So its momentum would be much easier to, or high momentum would be much easier to achieve. So 50 Nerf balls is more intense. There are more balls, but the one baseball would have more energy than one Nerf ball, and maybe even have more energy than all of the Nerf balls. So the photoelectric effect, evidence for quanta or quantization. So Einstein got the Nobel Prize for some work on this. Think about the video game analogy. So if we use like centavos, if we try to go into the arcade, centavo, like 25 centavo coins or whatever, those aren't going to work. We need to use peso coins. No matter how many of the small coins we use, it's not going to work. We need to use the peso. So here it's nickels and dimes, but those don't work. You need to use an actual quarter. You need a specific quarter. Like you can't put so many nickels and dimes in and then you'll get a quarter. No, you need that quarter. And that's kind of the same as the energy. You can't like throw together a bunch of low energy photons of light. You need one photon of light with sufficient energy, not like 10 photons which make up the same energy. It's got to be one photon only with enough energy. And so the evidence for this came from something called a line spectra. So gases can be excited, like using electricity even. And then once they're excited, they go to this excited state, and then they want to go back to the ground state again, the normal state, the neutral state. And at that point, they can release that energy as light. And sometimes we can see it, and sometimes we cannot. So electrons have more energy than normal. They haven't been removed yet. They're just higher in energy. As electrons go from higher to lower energy, light is emitted because remember the conservation of energy. Energy cannot be created or destroyed. Whenever they go from higher to lower energy, this energy has to do something. Some of it may be lost as heat, but most of it in terms of electrons is lost in as light energy. So the amount of light that goes in to excite them to the higher level is the same as the amount of light that goes out, usually, or in theory. So light emission spectra of excited atoms. So excited atoms emit light of only certain wavelengths. The wavelength of emitted light are unique to each individual element because each individual element has different numbers of electrons. It has different sort of atomic compositions. So the Bohr model made use of this idea of electrons orbiting the nucleus. It's an early 20th century, so early 1900s, and this was sort of the idea that the electron orbits around the nucleus. We know now that this is not exactly true. There are some problems with this, but it was a good step in the right direction. It was more than anyone else had come up with to that point. So any orbit should be possible, and so is any energy. But a charged particle moving in an electric field should emit energy. But this would, of course, result in the destruction of that atom, really. So this was a step in the right direction, but it wasn't much of a step. But we can also, it was somewhat modified, and Bohr asserted that line spectra of elements indicated that the electrons were confined to specific energy states called orbits. And so the orbits or energy levels are quantized, so such that only certain levels are allowed. So for example, we can have n is equal to 1, n is equal to 2, where this here is the n is equal to 1. So that's the most inner orbit. And so n is equal to 2 here, and n is equal to 3. Now we'll learn later that these are the principal quantum numbers. So this model is actually reasonably good at this point. So the Bohr model also contains an empirical relationship for the radius that it is from the nucleus. So how far is this distance? How far is this distance? How far is this distance? So on. So for example, we could do the calculation of for R2, so for when n is equal to 2, it could be equal to 2 squared times A0, which is 53. So this is 4 times 53 picometers. Oh, that's terrible. 53, which would be equal to 212 picometers for the n is equal to 2 level. It's just using this equation here. So atomic line spectra were spectra that were observed because there was light being emitted as the electrons went from higher energy to lower energy. So Bohr asserted that the line spectra of elements indicated that the electrons were confined to specific energy states called orbits. These are these circles which go around the positively charged nucleus. So the lines, colors, correspond to jumps or transitions between the levels. So for example, here we have 2 to 1, Here we have 3 to 1. We could have 3 to 2, for example. That's also a lot. Bohr said the classical view was wrong. So the classical view that, the energy could change continuously was incorrect, and it was true. So we needed a new theory for this, now called quantum or wave mechanics. These observables were what led to the classical view being disputed and then eventually being discarded for these very small things like electrons. And so we now have what's called quantum or wave mechanics. So electrons can only exist in certain discrete orbits called stationary states. Electrons are restricted to quantized energy states. And the energy of the state can be equal to minus the speed of light over n squared, where n is this quantum number, like n is equal to 1 is the closest orbit, n is equal to 2 is the next closest, and so on. Where n is the quantum number 1, 2, 3, 4. So atomic lines, spectra, and Niels Bohr. So light is separated into its component wavelengths by a prism or diffraction grating. I shouldn't have read that in that order. So this is a way of obtaining these atomic line spectra. So these individual lines. Here is the spectrum which is observed. And so there are only a few of these for each element, and they kind of form like a fingerprint for the element. They correspond to these transitions between the orbits. So here we have what's called a gas discharge tube, which just contains a gas such as hydrogen. You could also have neon or whatever. And this then has an electrical current passed through it. So it has like these two electrodes, and then an electrical current is put through this system. This electricity then excites the hydrogen in this case, and then it doesn't like to be excited, so it loses some of that energy and relaxes down to the ground state. And then this relaxation, it's absorbed the energy in the first place to become excited, so it has to release that energy in order to go back to the ground state. And so when it goes back to the ground state, it releases the energy as light, and so this can then be concentrated using these narrow slits. And so we end up with a very thin beam of light, which is incident on this prism. And then as the light passes through the prism, it is diffracted such that it is split up into its individual components. So it kind of looks pinkish here. And so this pinkish light then corresponds to like a red line, a green line, a cyan line, and a blue line. And different elements have different fingerprints. So for example, hydrogen has about 4 that we can see in the visible range between 400 and 700. There are also some that we can see in the slightly UV, because our eyes can also see a wee bit into the UV, but only a little bit. And then Mercury then has a lot more lines. They are usually quite different from those of hydrogen. They correspond to those transitions between the orbits. And then neon as well has a different fingerprint. Some of the lines are similar, but ultimately there's enough of them that are different that you can form a fingerprint. It's like, our fingers, our fingerprints, some of them have maybe similar lines to other people, but whenever you put the whole thing together, you'll see that each